probably my favorite problems that I found recently, right? This is the kind of problem where it addresses the two most important parts of being a software engineer. Can you write code that works? And are you capable of reasoning? Right? Can you think through a problem? And what this problem doesn't do is that one thing we all hate, right? It doesn't do that one thing we all hate, which is, do you know this little data structure algorithm trick, right? That's the most frustrating thing about any Leetcode style problem in an interview. It's like, well, I haven't learned this trick, right? They ask you a question like, oh, balance this binary search tree or whatever. And you're like, I don't know how to do that. And I've been working in the industry for 10 years and I've never known how to do that. I've never had to do that. So you're going to downgrade my likelihood of getting this role because I don't know some little trick. This problem is nothing like that, right? This problem is dependent on your ability to program and dependent on your ability to reason through problems. And it's not dependent on that thing that we hate, which is data structures and algorithms, right? It's not independent of code, not independent. It's not based on that. Demonetize me. What do you think I care about 4 cents? Okay, so you are given two integers, m and n, representing a zero index m and n grid. Okay, so there's m rows and n columns. Never a bad idea to kind of remember that and remind yourself of what that really means, right? So, there's these m rows here, and then there's these n columns here. Okay, you're also given a 2D integer array guards and walls, where guards of I equals row of I, column of I, and walls of I equals row of j, column of j, right? So you might have a guard in this position, right? And that's based on its, if a guard equals here, row I, col I, right? Well, that would mean that we're this distance, col I down, and we're this distance, row I to the right. And maybe we'll add a little color for the kids. The kids need color, right? The kids gotta have some color, man. And this is just getting boring. So let's add some color to this. That's a terrible contrast of colors. Okay, represents the positions of the ith guard and the jth wall, respectively, right? So I have a guard. It's at this position, so I know, okay, it's at this row. It's at this column. All right. A guard can see every cell in all 4 cardinal directions. So north, east, south, and west, right? So it can see everything above it, right? So this guard, its visibility, right, would be everything above it, everything below it, everything to its left, and everything to its right. And I guess itself, I don't know, right? Unless obstructed by a wall or another guard. So it's possible that we have a wall in some other position, right? Let's say there's a wall here. Well, then this guard can't see past this wall, right? So it's this wall is obstructing its capacity to see past it. So this is a space here that's open. A cell is guarded if there is at least one guard that can see it, okay? Return the number of unoccupied cells that are not guarded, okay? So that's the number of cells where the guard can't see, right? So in this example, just to make it clear, what cells can the guard not see? Well, the guard can obviously not see things that are not, up, down, left, or right from it directly. But also, it can see this portion. It can't see this portion here because the wall is blocking it. Okay, so let's go through a quick example. I'm not going to show you this directly. I'm going to do it based off of what's given here so you can see how you construct this little system. All right, so we have m equals 4, n equals 6. So we have 1, 2, 3, 4 rows, and n equals 6. 1, 2, 3, 4, 5, 6. Now I'm going to just box this in so you can see the dimensions of this perfectly. All right, so that's, we have m equals 4 here. I don't know what that m was. I apologize about that, guys. So that's m equals 4 and n equals 6. Okay, and then we have the positions of all of our guards. So our guards are at 0, 0. So I go 0 down, 0 to the right. We have a guard at 1, 1, so 1, 1. And we have a guard at 2, 3, right? So 0, 1, 2, 0, 1, 2, 3, right? So 0, 1, 2, 0, 1, 2, 3. Is that right? Guard, guard, guard. All right, I just want to make sure, right? Walls, 0, 1. 0, 1 is a wall. 2, 2 is a wall, so 0, 1, 2. 0, 1, 2 is a wall. And 1, 4 as well. 1, 1, 2, 3, 4. All right, is that right too? Okay. Now the easiest way to do this, 0, 1, 2, 3, 4. I can't 0, 1, 2, 3. Starting at 0, starting at the top corner, I always mess up, right? So So, that's a good thing about problems, right? Is you should write it out, but then you should also verify, right? Don't just write this out because then you might not understand the way that the information is given, but still use this to verify that what you're doing is correct. Okay, so we're trying to find the total number of unoccupied cells. Well, what would be the easiest way to do this? I think the most intuitive thing here to be thinking about this logically says, well, we want to find the cells that can't be seen. Well, then let's figure out what cells can be seen, right? So what is this guard going to contribute to the system? Well, this guard, it can't look up because there's nothing, right? You can imagine that these are all just walls, right? You could conceptualize this as, all right, these are all walls, right? I don't know why I'm doing this, but, technically these are walls on the edges. Right, so you can't see anything above. What I'm doing here doesn't make sense. I'm just saying, like, there's nothing above that I can see because there's just a wall there, right? Can't see anything here either because there's a wall there, right? You can think of these cells literally as being extensions of this, right? So these are kind of like, these are walls, right? What these walls do when they get in the way. All right. How about left? Left is the same deal. It can't see anything. But down, it can cover some space, right? This guard can see some space here. All right. Now let's look at any guard. We can do guards arbitrarily. Maybe we'll go in the order that we guards here. We see here. Okay. There's next one is at 1, 1. So up, again, there's a wall. There's nothing. Left, it can see the same space that this other guard can, right? So doubling up, I don't know if there's any added benefit there, right? We're just trying to think about the number of cells that aren't seen, right? It can see all of this left, and then it hits this wall. And then finally, we have this last guy. Can see all the way up. Oh, this guard, I forgot. This guard, everything right. So up, nothing, wall. Left, a cell that's already covered, but it can see that. Down, it can see here. Apologize about that, guys. Sometimes all over the place. Okay, up, it can see that way. Left, hits this wall. Right, it can see all the way here. Down, it can see here. Okay. So then our available so then really the problem just becomes, okay, now what cells are still not seen? Like we've looked at all the guards and we've calculated everything they can see based on what's in their way in all directions and what is remaining, right? So this cell has nothing, 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 this cell has nothing. So that results in 1, 2, 3, 4, 5, 6, 7. So the answer is 7. Okay. And then there's a pretty extreme example here, right, where there's a guard and every direction is covered. So there's 4 cells that are unseen, right, because it can't look up, can't look left, can't look right, can't look down. And these 4 cells are chilling. They're chilling like a villain, straight killing. I'm a trillin' villain, selling penicillin to the children. Okay, so, right, it's a pretty simple problem, right? It's pretty intuitive. It's pretty clear what it wants. It's kind of just like, how do you write code that does this? Well, all we really need to do, right, is we can just, in order to find this, what did we end up doing, right? We just looked at each guard. We looked at everything it covered. We did that for all guards. And then we said which cells are available at the end. So we should probably make some sort of system that says this C equals the cells in the grid. Do they call it a grid? Always use the right language. It shows your interviewer that you're willing to use the nomenclature that they prompt you for. Cells in the grid. Okay. And then I'll look at each guard, G. And I'll just say, okay, for each direction, I'll look in each direction, right? So I'll look at this guard. I'll look left. Keep looking. Until what? Until wall or guard. Right, so that's all I really do, right? I look at this guard. I go left. I keep looking until I hit a wall, then I stop. Then I go to the next direction. I look up. I hit a wall. I stop. I go to the next direction. I go down. And I hit this cell. And I say, okay, add grid cell to C. Terrible writing here, right? So I had this one, this one, this one. I hit a wall, I stop. I try the other direction. I hit a wall, I stop, Okay, now I'm done with this guard. I look at the next guard. I look up, nothing. I look left. I hit a cell. I add that grid cell to C. Note that that cell would already be in C because there's a double intersection. I look down. I look right. I hit this wall. I'm done. Look at this guard. I look up, look right, look down, hit a wall. I'm done. All right. So that's all we really have to do to make this work. All right. So now what this really becomes about is, well, how do we program it and how we do this efficiently? Now, this would work, right? So we have to look at all guards, right? So this would be O of G. I'm going to say G is the number of guards, right? And then we have to look at all 4 directions, okay? Now we have to keep looking. So we could look in either N or M locations, right? Because if I start here, I can keep looking all the way down, can look all the way right, or all the way up and all the way to the side. Or if I'm in the middle, I could look here or here or here or him. But in the total, I'm going to be doing actually not max of N plus M operations, okay? This is O of 4. This would be O of N plus M, right? Because no matter where I'm at, I'm going to go, I could, the max, worst case, go all the way up, go all the way to the right, all the way to the left, or all the way down, okay? And then I have to look until I find a wall or another guard. So how would I find out if I'm looking at a wall or a guard? Well, I can add all the walls and the guards to this C system. So I can say if this wall, I would say like C of the wall's position of X and the wall's position of Y. C in the wall position of X, wall position of Y equals, I don't know, obstruction or something. And that would mean that there's something in the way. So I could do this in constant time if I pre-process where all the walls and all the guards are, right? So I basically say like, if the position that I'm at is equal to one of the positions of the guards, and I put it in a system where I can instantly check like a set or a hash list, I could do this in O of 1, 2, and I could do this in O of 1, 2. Okay? So what does that give me in terms of my runtime? I have guards times 4 times N plus M. So that's 4G and, what am I doing? So that's big O of G of N plus M. Okay. Big O of G N plus M. Okay, what is this other one? So M times N, so this is where there's constraints, because there's another way you could do this. I'm actually going kind of free fall right now, because I'm kind of freestyling this, because this isn't actually the way that I solved it, so I'm kind of curious about what the benefits are of doing it this way versus another way we can also do it. So guard's length is less than, of course, it's less than M times N, but it's less than 10 to the 5 times 10 to the 5 plus 4. Okay, so G is always less than or equal to 5 to the 10 times 5 times 4. And then M times N is always less than or equal to 10 to the 5. Okay. If M times N is less than 10 to the 5, then M plus N is less than 10 to the 5. But M or N could be less than or 10 to the 5. So in the worst case, M is less than 10 to the 5, or N is less than or equal to 10 to the 5. So that means you could get GM times, I'm going way too far into the math here, trying to figure out what's the optimal solution, because this way might be actually a little bit slower now that I'm looking at it, right? Because that could be GM plus GN, 5 times 10 to the 4. So this could be 10 to the 9, which far exceeds what's possible. So this solution here, although it works, the fact that we have this G times N plus M, and the way that these constraints are set up, you know, you can review this if you want, but basically we could get 10 to the 9, right? Because you have G times N plus M, where G could be 10 to the 4, M could be 10 to the 5, 5 times 10 to the 5 times 10 to the 4, GM plus GN, 10 to the 9, right? So it's way too big. So is there another way we can do this where this isn't so slow? Okay, so maybe what we'll do instead is let's look at this again, and let's just try to think about, okay, you know, let's try to think about, there's another way we can do this that's a little bit quicker, perhaps. All right. So what about instead if we just did a rolling kind of system here? Okay. Now I think you can actually prove that this is not that slow because of the positions of things. But the proof with this to get rid of factors is a lot more difficult because really none of these would go all N or M because things could be in the way, right? So I don't really know what the limits are there, okay? But what about if we just think about this like the following? What if we start here and we say, okay, we see a guard, all right? So I know I see a guard. Then I go to the right and I say, you know what? Okay, so there's a guard. What if I just solve the problem like the following, okay? So I look at this system and I wonder why everything is so off. Is that even what it was initially? Yes, it was. All right. Oh, because I'm an idiot and I didn't centerize this. Now these are all off. See how life works like that? You mess up beginning and then you make more mistakes instead of just going back and fixing what you were doing. So what if I just do this? I say I see a guard and I'm going right. Let's say I'm going right. I'm right centric, okay? I look at this guard and then I see a wall. Now that I see a wall, I know I'm in the clear. Why am I in the clear? Because as soon as you see a wall, it blocks anybody from the right. So I'm thinking about just going right. So from going right here, going forward, I'm good. Starting here, I'm good going right. And then I see a wall. And then I'm bad, bad, bad. But then I see a guard. And then I see a wall. And then I'm good going forward. I'm good going forward in the beginning. I see a wall. I'm good. I see a guard. I'm bad. And I see a guard going forward. I start a new row going right. I see nothing, 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 nothing. Okay, that's my first iteration. Now let's do this again. So we'll call this going right. Now let's play this game again. But now we will go, let's say down. All right, now you'll see in a moment why we're doing it like this. So going down, I see a guard. And again, I'm not centering things, and I don't know why I keep doing that. Okay, I see a guard. Going down is bad, bad, bad. I see a wall, we're good. But then I see a guard again, so we're bad, bad, bad. I see nothing in the beginning, right? Going down, down. I see a wall, we're good. I see nothing, we're good. I see nothing, nothing. I see a guard. That's bad. And that means a guard covers this going down. I see nothing going down. Good. Wall. Nothing, 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 nothing. Right. Now, that's going down. You might be looking at this and be like, isn't this more inefficient? But that's the beauty of programming. Sometimes solutions that to you on paper might seem more inefficient if you actually look at the implementation and what the repercussions of that are. It's actually faster. It's actually faster. Is that crazy? It's actually faster. All right, so then we'll do, we'll go, which direction we go now? We went right down, let's go left. So going left, I'm good in the beginning, boom, 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 boom. And then I see a wall. Again, I'm always good in the beginning, wall. I see a guard. You might want to fast forward through this game. I see nothing. I see a guard going left. The guard is instantly blocked by this wall. And then I see nothing. All right. Now let's do our last one here. I'm not even going to worry about it not being on. Just fuck it. Screw it, man. No. It must be right. Okay. So what's my last direction here? I need to do up. Of course, up. So going up, you assume good. You assume good. Oh, I see a guard. But then it's instantly blocked going up by this wall. Wall, good. I see this guard. Blocks these cells. Wall, good. Nothing, good. All right. So now I kind of think about it, instead of like looking at each guard, I'm kind of just sweeping through the system, going left, going up, going right, and going down, right? And from that, I say, okay, well, these are 4 different pictures. Well, if it's red in any picture, it's red in the solution, right? So if I add all these together, right, using that idea, well, you know, I'm adding these together and the resulting system is what's possible. Well, if in one of these directions sweeping through a guard can see a cell, well, then the guard can see it in all directions, right? Now, of course, the guards themselves are all red. And the walls, they don't count for anything. This should be centered. Ugh, come on, man. Come on. Do it right. All right. So here, I mean, even though the walls are, I mean, I'm going to make the walls red because they don't count as cells that you can see, right? And the cells you can see are green. So, you know, let's just add in the red cells from all these systems, right? So this is red, red. Red, red, and red. Okay, there's red, 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 red. How about in this system? Red, 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 red. Okay. So 1, 2 here. This is a lot harder than it seems. And then this is this down. Down, down, and down. And that would mean that the resulting cells. Did I do all the down? Oh, I forgot. Wait, messed that up. This is down, right? So mapping this down. And then what's remaining is just what's green. You'll notice that that's, you know, the answer, 7. So you might be like, well, that was an over-convoluted way of doing something that it seemed like it was more efficient before, right? This approach seemed more efficient, yet you're telling me that we need to do something different here, and it's weirding me out, right? Saying that we need to do this super convoluted, complex solution, yet it seems harder. Well, what did we really have to do to make this work? We went, instead of doing what we did before, what we're going to do is we're going to go each direction, for each direction, for each row, for each column, check guard, wall, or nothing. That's all we did here. We looked at each row, we looked at each column, and we checked if there was a guard or a wall or nothing. Okay? So we just slide through. If we see a guard, then we continue saying there's a guard that can see until we see a wall. And we do that in each direction. So what this does is when we look at all directions, how many directions are there? Where there is O of 4 directions. We look at each row, how many rows are there? There's M. And then how many guards, how many columns are there? There's N. And then how do we check this? Well, we said we could do this in constant time, and I haven't really gotten to the details of that, but I'll show you in a moment. So that's O of M times N time, right? So this is O of 4mn, which equals O of mn. So you might be looking at this and saying, oh, well, this looks a lot more complicated, but really this is O of mn. And this solution is O of gm plus gn. And depending on the constraints, this might actually be faster. Or this might be faster. But since m times n is always less than 10 to the 5, that means that when we do our little comparison here, our first solution is g of n plus m, which is going to be less than or equal to 10 to the 9. Right? Because g is less than or equal to 10 to the 4, and n plus m could be 10 to the 5. So that's 10 to the 4 times 10 to the 5. I guess there's another factor of 5 here, but I don't really care. Less than or equal to 10 to the 9, right? Versus n times m. Well, that's just given right here, less than or equal to 10 to the 5. And this will be 4 times 10 to the 5 versus 5 times 10 to the 9 or whatever. But, you know, looking at these two solutions, the way that the constraints are given, this one, although it's far more intuitive, it's 10 to the 9, while the one that's a little bit more strange and on paper, when you write it out, seems harder, is 10 to the 5. So it's a beautiful lesson in complexity, right? Just because something is seemingly uncomplex in the simple case, it might actually be far more complex in the complex case, in the, you know, compute exhaustive case. Okay. So that is pretty much this problem, all right? Now bear with me for a moment because we're going to create my screenshot. All right. So how do we actually code this up? So we should probably keep track of the things that we've seen, right? So I'm going to make that a default dict. So what I'm basically saying is, you know, this is the stuff. How are we going to do this? If it equals 1, it's always hard to know how you're going to do this. So if it's 1, that means that the guard can't see it. So we'll assume that all the cells the guard can't see, and then when we pass through the system, we'll paint them red corresponding to the guard being able to see them. Okay? And now we're going to look at all directions, right? So we want to look at all 4 directions. So if you want to go directions, we can go right, left, up, and down. All right, so how do we go right in the system? Well, we're going to look at all rows. And how many rows are there? There's M. And then we're going to go right, so we're going to look at all columns. And there are many columns are there? There's N. How will we go left? To go left, we could do the same thing with the rows. So we could, I'm not going to do that. I'm going to do it here. So we look at all columns in range. So we all still looking at all the rows. When we started a row, we go right. Start the next row, we go right. Start the next row, we go right. Here we could look at all columns, but we want to go left, right? So we look at all rows, but instead of going right, we go left. So we start at the end of the array and go our way back. So that would be left here, actually. And then what about up, down? Well, up, down would just be kind of these switched. So instead of starting looking at each of the rows, we look at each of the columns. So this would be right. I guess it makes a little more sense that it's here. This would be up. Wait. I always get confused here. So we look at each column, and then we increase the rows. Right, so this would be going down, actually. Right, because you start at the top and then go down. So we look at each column, and then we go down. And this would be up, which would be the opposite thing. Each column, go down. Then we look at each row, and we go up. It's always hard, because, like, the other thing is, like, you don't really need to think about how the directions are made as long as you can make all 4. So I know, like, I'll do M to N minus 1 to -1, N to M minus 1 minus -1, right? So I know I have to make all these loops to get all the directions, but sometimes I forget, like, wait, is that actually going up or down? It doesn't really matter as long as I capture the direction. Okay? Now, the guards, right, and the walls, the guards and the walls and the smalls and the balls and the talls and the calls. So in here, I could just say, I could look at each guard's position and guards, and I could say, okay, C at this position equals a guard. And I could look at all XY positions of wall, and I could say C of XY equals a wall. All right. That's the beauty of using a default dict. So someone might scream at this and saying, you know, you're using like different data types inside of your default dict, but guess what? That's Python, baby. I can do whatever I want. All right. So for right in range M, for C in range N. So we'll first assume that there's no guard, which we should always assume. And we could say, well, if this is a guard, what does that mean? So if C of XY equals a guard, then guard equals 1. Else if C of XY equals a wall, then guard equals 0. And then we say, well, if we're dealing with a guard and C of XY isn't the guard itself, then we're going to say that this value can be seen by the guard. So what I'm basically saying is like, all right, if there's a guard and I'm not actually on the guard cell, then I can see this value. So like what's really happening is, let's say, imagine going down, right? I set guard equal to 1 because I have a guard here. Now on the same cell, I don't want to set this to 1, validating that it's red, meaning that it's 1. But then when I get here, what happens? I say, is this thing equal to 1? Guard? No, this is a blank cell. Is it a wall? No, it's still a blank cell. So therefore, the guard can see down, right? Because the guard's going to be obstructed when it sees a wall. If it sees another guard, then the new guard will continue seeing, so it's still guard equals 1, right? If there's a guard and a guard, well, as long as it's not the guard itself, it'll continue seeing. Does that make a little bit of sense? Maybe you should review this a little bit, what I'm doing. Watch closely, right? But that's the basic idea. All right? And then we just do this for each range. But of course, we need to reset G to be 0 each time. And at the end, we just return the sum of, this cell equaling 1 for x in range n, for y in range m. If this equals... Oh, I forgot to do double equal, guys. That's why you don't copy paste. Look at that. Now I have to show my embarrassing mistake over and over and over again. And it's probably not the only one because it's a pretty simple thing that I messed up. So, let's see. 19. Ooh. So I messed up. Oh no, if it's red, that means it's 1. Well, it's default to 1. Ish. Okay, let's make this 0. So 0 means that, I apologize, guys. And again, see, since I'm not modularizing this, I have to show my mistake again. So if it equals 0, that means it's red. And at the end, we'll sum all the ones that are still 1. And all the ones that are still 1 will be the ones that haven't been set to red by the guard seeing them in any of these cases. Eesh. See, I'm telling you guys all this. So this is a good problem because it shows you how to code, and I can't code, apparently. Isn't that a beautiful thing? So if it equals 0. No, if it equals 1. Because if it equals 1, it hasn't been seen. Oof, I'm struggling. All right, let's see. Why did I do XY here when it's supposed to be RC? See, what I'm really trying to do is I'm just trying to show you guys lessons of why you should modularize your code. Right? Because now I'm doing this over and over and over again. I do this a lot. I mean, it's an excuse, right? But it's like, when I explain things as I'm doing them, I tend to make more mistakes. I promise I am not this sloppy. But, being sloppy doesn't really matter that much if you can show that, okay, I'm nervous. So that's why I keep making all of these mistakes. But I'm just nervous. What, a guy can't be nervous? What? I'm not allowed to be nervous? Why does it keep I keep doing it 3 times? Okay. Should do it 4 times, just 4 directions. 10. 10, 10, 10, 10, 10, 10, 10. 10 is weird because there's 3 guards. Ten is such a weird number here. So somebody out there knows what I'm doing wrong here, and they're like, no, you idiot. You idiot. You are the chosen one. You guys tell me, why is it overcounting the guards here? Well, there's also 3 walls. Yeah, but if CRC equals a wall, G equals 0, so then this is 0. Ah! All right, read this closely. R in range M, C in range N. n minus 1, negative 1, negative 1. Okay, that looks good. C in range n, R in range m. R in range m minus 1 to negative 1, yep. CRC, 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 CRC. Defaults to 1. XY and guards, XY and walls. Let's print out actual C. So let's see what this thing's. I don't know how to print that, Siri. So let's Alexa. So let's see what this thing thinks the system looks like. So 0, 0 is G, 1, 1 is G, 2, 3 is G, 0, 1 is W, 2, 2. 2, 2 is W, 1, 4 is W, 0, 2, 0, 1, 2, 0, 1, 2 is 1, but it should be 0. So down direction doesn't seem to be working. Are all the walls still intact, right? So I don't want to make sure I'm not overriding a wall. Oh no, that's 0, 2. Ah, guys, I'm sorry. 0, 4 is 1. 0, 5 is 1. 1, 0 is 0, yes. 1, 2 is 0. 1, 3 is 0. 1, 5 is 1. 2, 0 is 0. 2, 1 is 1. 2, 0, 1, 2, 3, 4. Is 0, 2, 5 is 0, 3, 0, 0, 3, 1 is 0, 3, 2 is 1, 3, 3 is 0, 3, 4 is 1, 3, 5 is 1. So what did I do wrong here, guys? What the hell? Oh, shoot. You gotta be kidding me. Gosh darn it. It always is screaming at you. But at least you see how that works, relates. It's all part of the lesson. All right, there we go. Terrible, terrible, terrible. And it's probably still wrong because apparently I can't do anything right today. All right, so we said that this one is O of M of N. All right, I already went through this whole thing, right? Because we do this. Now, I guess one thing I'll do really quick. I'm going to leave it like that. All right, I'm actually not going to. You can take this and you can put these all in functions. All right, this could all be in one function. And you can make this a lot tighter. And that also helps with the editing, right? Because before I was like editing this, then editing this, then editing this, and then editing this. Whereas if I put this in function and then just call it, I only have to edit it once. So that's just a important point about modularity, but I've already went way over time debugging my terrible solution. Okay, so time we said was O of N times M. And then for space, well, we actually have to keep track of the location of everything, right? Because we have to keep track of, okay, has it been seen? Has it not been seen? Is there a guard there? Is there a wall there? So that's also O of M and space, which is better than our old solution, which was O of G times M plus M. And now that I'm thinking about that old solution, you might actually need an extra factor of N times M because this takes N times M time too. So you might actually end up doing another N times M anyways. All right, guys, peace out.